A computer program called BonRoute was developed in the Research Institute in Bonn for obtaining routings of a chip. It is based on new mathematical research results. We will elucidate this algorithm briefly. If there are only 2 pins to be joined in the shortest way, the solution is easy. The routing planes can be envisaged as a grid graph in which parts are left out because they've already been used. A graph consists of vertices and edges, with the edges always connecting 2 vertices. A well-known algorithm of Dijkstra is guaranteed to find the shortest path in a graph. No vertex or edge is traversed more than once. This algorithm is, for example, used in navigational systems for finding the shortest route in a road network. For small graphs, like the German motorway network, Dijkstra's algorithm in its basic form is sufficiently fast. In the example shown, the shortest route from Bonn to Munich is determined using Dijkstra's algorithm. For more complete maps, showing other roads as well, one needs an optimized version of this algorithm. In chip design, the graphs are more than 1,000 times larger than all the road networks in the world combined. That is why Dijkstra's algorithm cannot be used in its basic form in chip design. One thing we can do is to use smaller regions in which we want to find a route. Another is to search only in the direction to the target and avoid exploring detours. Often we need to connect not just 2 pins by a path, but 3 or more pins by a Steiner tree. There are also technical criteria which must be met and which often make longer paths necessary. The above-mentioned reduction of regions has another advantage. It largely prevents nets routed earlier from being so unfavorably placed that later nets are completely blocked. This, however, requires that the reduced regions are chosen carefully. To determine these is therefore one of the most important problems, called global routing. In global routing, one divides the chip surface into rectangular tiles and then finds a Steiner tree for every net in such a way that no tile is too full. The tiles are envisaged as resources with limited availability. Every time we find a Steiner tree for a net, it will utilize some of the available resources. This will cause an initial rise in resource utilization, as the colors show. In order to prevent an indiscriminate use of resources, one gives each of them a price which grows exponentially as the resource gets used more and more. Steiner trees that utilize heavily used resources will thus become very expensive. This is especially true for fully utilized or temporarily overloaded resources, depicted here in red and black. If we repeatedly find an optimal Steiner tree in this way, we will obtain routings that will, at least on average, use no resource excessively, at least inasmuch as such a solution exists. One can prove that the number of Steiner trees that have to be calculated per net is very small. A mathematical formulation of this algorithm is shown on the left. This algorithm is so general that one can solve completely different problems optimally with it. We can, for example, also represent the power consumption as a resource, or even the limited times available for signal transport. As near-optimal solutions are guaranteed, the routings computed with BonRoute are far superior to other solutions.